Let us learn about the third property in this particular class. Okay, so every skew symmetric matrix of odd order is singular. Okay, what does it mean by singular matrix? Singular matrix is a matrix whose determinant is equal to 0. Okay, singular matrix is such a matrix. Singular matrix is such a matrix whose determinant is equal to 0. Okay, so every skew symmetric matrix of odd order is singular and even order is a perfect square. So let us have a look at the proof of this particular thing. So first of all, the matrix is skew symmetric matrix, and if it is of odd order, if it is of odd order means 1 cross 1, 1 cross 1, 1 cross 1, 3 cross 3, okay, 1 cross 1, 3 cross 3, 5 cross 5, okay, 5 cross 5, 7 cross 7, 9 cross 9, then such matrices, such skew symmetric matrices will be singular. Okay, that is their determinant will be equal to 0, and if the order is even, even order means 2 cross 2, 4 cross 4, 6 cross 6, okay, 8 cross 8, 10 cross 10. If such matrices are there, that is of even order and skew symmetric, then their determinant, is a perfect square. Their determinant is then a perfect square. This is what we need to prove. Okay. So let us suppose that A is a skew symmetric matrix. Let us suppose that A is a skew symmetric matrix of order small n. A is a skew symmetric matrix of order small n, where n equal to 2k plus 1. What does it mean by n equal to 2k plus 1? Okay, so n equal to 2k plus 1 simply means that it is odd number. Order is odd. The order small n is odd because 2k plus 1 represents odd numbers. 2k plus 1 represents odd numbers where k belongs to, just a second, k belongs to whole numbers, set of whole numbers. K belongs to set of whole numbers, that is k can be 0, 1, 2, 3, 4 like that. Okay, so if k is 0, n will be 1, if k is 1, n will be 3, if k is 2, n will be 5, if k is 3, n will be 7. Okay, so 2k plus 1 means odd number. 2k plus 1 means odd number where k belongs to the set of whole numbers, that is 0, 1, 2, 3, 4. K can be anything from 0, 1, 2, 3, 4, 5, 6, 7, 8 like that. Okay, so 2k plus 1 represents odd. So the order of A is small n, order of A is small n, and small n is odd number, and small n is odd number, and A is a skew symmetric matrix also. Then what happens? Let us have a look. Then A transpose is equal to minus A. From where? From definition of skew symmetric matrix. From definition of skew symmetric matrix, A transpose is equal to minus A. This is from definition of skew symmetric matrices. This is from definition. So let us suppose A transpose is equal to minus A. Let us suppose this is equation number 1. Let us suppose that this is equation number 1. If we take the determinant on both the sides, so what is this step? Take determinant on both sides. Okay, this is the step. Okay, so this particular symbol represents determinant. Okay, determinant. So this particular symbol, take determinant on both sides, that is this two vertical lines represent determinant. Two vertical lines represent determinant. Okay, so determinant of A transpose is equal to determinant of minus A, taking determinant on both the side of this equation. Now determinant of A transpose and determinant of A are equal. Determinant of A and determinant of A transpose are equal. This property we have already learned in the previous lectures. This particular property, that determinant of A transpose and determinant of A are equal. This property we have already learned in the previous lecture, right? Determinant of A is equal to determinant of A transpose. So A transpose can be replaced by A. Okay, instead of complete DET, you can also write it like this. Instead of complete DET for determinant, you can also write it like this. Okay, both are one and the same thing. So determinant of A is equal to determinant of A transpose. So here is determinant of A transpose. So we are replacing it with determinant of A. So determinant of A, the right hand side remains as it is. Right hand side has remained as it is. Okay. Now determinant of minus A, determinant of matrix minus A is equal to minus 1 to the power n determinant of A. Okay, this is a property which we had already learned in the previous lectures. Okay, this is a property which we had already learned in the previous lectures, that determinant of minus a is equal to minus 1 to the power n determinant of a. Determinant of minus a is equal to minus 1 to the power n determinant of a. This where n is order of the matrix A. Okay, where n is what? N is what? Small n, where small n is the order of matrix A. Okay, so determinant of minus a is equal to minus 1 to the power n times determinant of A, where n, small n is the order of matrix capital A. So we have replaced it, this minus a, replace this minus a, determinant of minus a, this particular thing, that this and these are same, this thing and this thing are same, this thing and this thing are same. So we wrote it like this thing can be written like this, but n is 2k plus 1, n is 2k plus 1, n is equal to 2k plus 1, so it will be minus 1 to the power 2k plus 1 determinant of a. Minus 1 to the power n will be there initially, minus 1 to the power n will be there where n is the order, minus 1 to the power n will be there where n is the order, but n is equal to 2k plus 1, n is equal to 2k plus 1, so we are writing 2k plus 1. Okay, so minus 1 to the power 2k plus 1 determinant of a. Now have a look, minus 1 to the power odd. Okay, 2k plus 1 is an odd entity, 2k plus 1 is an odd entity, minus 1 to the power odd is equal to minus 1. Okay, and minus 1 to the power e1, this thing you must keep in mind, minus 1 to the power e1 is equal to 1 plus 1. Okay, minus 1 to the power e1 is equal to plus 1, and minus 1 to the power odd, minus 1 to the power e1 is 1 and minus 1 to the power odd is minus 1. Okay, so over here it is minus 1 to the power odd, so it will be minus 1. This particular entity will come out to be equal to, it will come out to be equal to minus 1. It will come out to be equal to minus 1. So what did we get? What did we get then? We got this determinant of a is equal to determinant of minus a. We got determinant of a is equal to determinant minus determinant of a. Okay, determinant of a is equal to minus determinant of a. Determinant of a is equal to minus determinant of a. Now a is equal to minus a. So if you take this to the left hand side, if you take that to the left hand side, what will happen? Something of this kind will happen. Okay, something of this kind will happen if you take this to the left hand side. Okay, which will be equal to 0. But two times, when same quantity is added 2 times, when same quantity is added 2 times, what happens? It is 2 multiplied by that quantity. Okay, is equal to 0. So this is the fact which we got, but we can exclude 2. So determinant of a is equal to 0. We can divide both sides by 2. Divide by 2 on both sides. Okay, so when you divide this particular thing by 2 on both the sides, you will get determinant of a is equal to 0. But when determinant of a matrix is 0, when determinant of a matrix is 0, then we say that the matrix is singular. Okay, when determinant of a matrix is equal to 0, we said that the matrix is singular. The matrix is singular. So matrix A is singular because its determinant is 0. As the determinant of this matrix is 0, so matrix A is singular. Okay, this is very much clear. So therefore every skew-symmetric matrix of odd order is singular. We have successfully proved this. Every skew-symmetric matrix of odd order is singular. Every skew-symmetric matrix whose order is odd, of odd order means whose order is odd, that is singular. Okay, now let us have a look at the, okay, every skew-symmetric matrix whose order is odd will be singular. Okay, so that is the thing. And even order, if the order is even, then it will be a perfect square. Now this is even order skew-symmetric matrix. This is a skew-symmetric matrix clearly, because if you take its transpose, that will come out to be equal to minus a. So this is clearly a skew-symmetric matrix. Okay, and what is the order? 2 cross 2 is the order of this skew-symmetric matrix. 2 cross 2 is the order of this skew-symmetric matrix. If you try to take its determinant will be what? Determinant of A will be equal to like this. We will write it like this. Okay, now if you take its instead of det you can also write it like this. Okay, instead of deta you can also write like this. Instead of deta you can also write it like this, two vertical lines. Okay, both are one and the same thing. Okay, so determinant of a is equal to 0 minus 2 into minus 2. Okay, because this multiplied by this minus this multiplied by this, so this is the expression. So determinant of a is equal to 4, but determinant of a will be equal to 2 square. It came out to be 4, but 4 is 2 square. 4 is 2 square, so determinant is a perfect square. So determinant is a perfect square. So we can say that for the determinant we can say like this, that the determinant the determinant of a skew symmetric matrix, determinant of a skew symmetric the determinant of a skew symmetric matrix the determinant of a skew symmetric matrix of even order. Okay, the determinant of a skew symmetric matrix of even order is a perfect square, is a perfect. Okay, so the determinant of a skew symmetric matrix of even order is a perfect square. Okay, and if we talk about odd order, what will happen if the order is odd? If it is odd order, then determinant is equal to 0. If odd order, then determinant is equal to 0. So this is what we can conclude. From the study of today. So this third property has been successfully discussed. Okay, from the fourth property onwards we will study in the next class. This is the fourth property. From here onwards we will study in the next class. Okay, from here onwards we will study in the next class. So thank you very much. Please like and subscribe. Thank you very much.